ever wondered if we could upload our minds just like computers back up files to the cloud? This isn't just science fiction anymore. Welcome to Skill Render, where today we explore brain-computer interfaces, BCI, the real tech that connects our brains to machines. Let's start with neural interfaces. These are systems that create a direct communication pathway between the brain's neurons and an external device. Think of it as a translator between your thoughts and a machine. Neural interfaces can be invasive or non-invasive. Invasive ones implant electrodes into the brain tissue, allowing for precise signal capture. Non-invasive interfaces, like EEG headsets, sit on the scalp and are more commonly used due to lower risk. Electroencephalography or EEG is a non-invasive method of recording electrical activity of the brain. EEGs measure voltage fluctuations resulting from ionic current flows within neurons. Different brain wave patterns like gamma, beta, alpha, theta, and delta correspond to different mental states. Engineers and neuroscientists use these wave patterns to detect user intention, such as moving a cursor or controlling a prosthetic. But raw EEG data is messy. That's where signal processing comes in. Engineers filter out noise, amplify weak signals, and use algorithms like fast Fourier transform to analyze brainwave frequencies. So moving a robotic arm just by thinking is possible, but it is a complex process. That's exactly what brain-computer interfaces, or BCIs, are making possible. It all starts with brainwaves, tiny electrical signals produced by neurons in our brain. When you think about moving your arm, your brain generates a distinct wave pattern. These brain signals are picked up by sensors and sent to a computer. But since raw brainwaves are messy, the computer has to clean them up, amplify them, and run them through algorithms that can recognize specific patterns. The computer translates these patterns into a digital signal, often using binary code, so it can understand what you want to do, like opening or closing a hand. Finally, the computer sends that signal to a robotic prosthetic. The result? A smooth, physical movement, powered by your thoughts. This is more than science fiction, it's real technology, changing lives by turning thought into action. And it all begins with understanding how our brains talk to machines. Machine learning models are often trained to recognize patterns in the signals. With enough training data, these models can predict what the user is trying to do based on EEG inputs. To interpret brain signals, we also need to know where they come from. Brain mapping links brain regions to functions like movement, speech, or memory. The motor cortex, for example, lights up when we think about moving. Tools like fMRI and Magnetoencephalography complement EEG by giving spatial resolution. Combining these helps refine how and where BCIs listen to the brain. fMRI measures brain activity by detecting changes in blood flow. When a part of the brain is more active, it uses more oxygen, and blood flow to that region increases. fMRI tracks these changes using a signal called BOLD, blood oxygen level dependent. MEG, Magnetoencephalography, measures the magnetic fields generated by the electrical activity of neurons in the brain. These fields are extremely weak, so MEG requires very sensitive detectors called SQUIDs, superconducting quantum interference devices. One example of machine learning models are neural networks, modeled after the human brain. In a BCI system, they help detect patterns in brainwave data like when a person is thinking move right. Classify intentions like walk, grip, blink and predict outputs even when signals vary from person to person. They're trained using labeled brain signal data, so the model learns how different mental states or commands appear in EEG or fMRI data. Deep learning is a subset of neural networks with many layers. It's especially powerful in BCI because it can extract features automatically from raw signals, no manual filtering needed. It can model nonlinear, complex relationships. It works well with large datasets like hours of EEG recordings. It powers real-time BCI applications, such as controlling wheelchairs or drones, communication devices for paralyzed patients, gaming, or neurofeedback systems. Let's explore how brain-computer interfaces, neural networks, and deep learning work together to turn thought into action. It begins with a single intention, say, move hand. That thought generates electrical signals in the brain, which are captured by an EEG headset. These signals are often faint and cluttered with noise. To make sense of them, the data is amplified, cleaned, and digitized, ready for interpretation. This is where artificial intelligence steps in. A deep neural network analyzes the signal and deciphers the user's intention by detecting subtle patterns. Once the intent is recognized, a command is generated and sent to a device, like a prosthetic hand, which responds by moving, precisely as the user imagined. From invisible brain signals to visible action, this is the promise of BCI technology powered by machine learning. Behind the scenes, 3 components make this possible. Neural networks identify patterns in brain activity, decoding mental tasks like imagine movement or focus. Deep learning, a more advanced form, goes even further, processing raw, complex, and highly variable brain data with remarkable accuracy. And the brain-computer interface brings it all together, translating neural data into meaningful, real-world commands. This collaboration between the brain and technology is what makes it possible to control machines with nothing but a thought. So, what does the future hold? Brain-computer interfaces could allow people to control devices with their thoughts alone. Companies like Nueralink are working on high-bandwidth, implantable BCIs for everything from paralysis treatment to enhanced cognition. Imagine a world where you compose music, write code, or even communicate emotions just by thinking. Ethical questions arise too: data privacy, consent, and mental health. The future is promising but must be handled responsibly. So the question remains, can we download our mind? Not quite. The human brain isn't like a hard drive. Our thoughts, memories, and sense of self aren't stored in files. We're far more complex. While brain-computer interfaces can read brain signals to control a device, they don't capture who we are. Consciousness, what makes you you, remains one of science's greatest mysteries. Could we one day build a digital version of ourselves? Maybe. But it wouldn't be you, it would be a simulation trained to act like you. So instead of downloading the mind, today's technology helps us extend it. Communicating through thought, enhancing memory, and interacting with machines in ways once thought impossible. We're not uploading our minds. We're unlocking them, one signal at a time. Thanks for watching Skill Render. If you liked this video, give us a thumbs up, and don't forget to subscribe for more STEM-powered explorations.